All right. Hi, everyone. I hope you can hear me. Let's get started. So just let's start with a recap of where we were last time. So last time we studied one-way functions. And very roughly, one-way functions are functions which are easy to compute but hard to invert. So easy in one direction but hard in the other direction. And we also saw a construction of one-way functions based on the factoring assumption, right? It was not a very difficult construction, and we were even able to prove the security of the construction based on the factoring assumption. But a major limitation of one-way functions is that we don't know what they would leak, right? The only guarantee with one-way functions is that they don't leak the entire input, but they might leak half of the input, they might leak even more than half, and things like that, right? So this is a major limitation which we will sort of try to overcome right now. So a limitation is that one-way functions might leak a lot of the input bits. In fact, for all we know, they might leak almost all of the input bits, and just some of the bits might remain, right? So now our goal eventually is, of course, to construct things like encryption schemes, right? In encryption schemes, we want the message to be hidden entirely, right? Even if an encryption scheme leaks like a single bit of the message, we are not happy with that. And our eventual goal will be to take techniques which we developed in the context of one-way functions and build bigger and more beautiful primitives. Like encryption is one, but today we will focus on pseudorandom functions and so on. So let's just try to think about how we can overcome this limitation. Okay, fine. One-way functions might leak a lot of the input bits, but is there some subset of the bits, or even let's say one bit? Is there even a single bit in the input which I can point to, and I can be confident that, hey, my one-way function is going to keep this bit hidden in some sense, right? So that's the question. So is there any bit of the input x which the one-way function f will not leak? Okay, and I'm not going to define formally, but by leaking, you could think of it as as enabling an adversary to guess this bit with probability clearly better than half. Okay, so now the first observation is that it's actually very easy to design one-way functions which don't leak some specific bit. So you can always design a one-way function f prime given f such that, let's say, f prime doesn't leak, say, the first bit. And how does f prime work? F prime takes as input some bit b concatenation x, and then just outputs f of x. Okay, so f prime takes an n+1 bit input and just ignores the first bit and applies the one-way function f to the remaining n bits. And here you can see that f prime clearly hides the first bit b. But this is a specific one-way function, right? So this is not what we are talking about. So I'm given an arbitrary one-way function f. The question is, can I point to any specific bit, let's say the ith bit, which f hides. Okay, so any thoughts about that? Can I point to any specific, let's say the ith bit or whatever? You can choose the value of I, so that I'm sure that the one-way function f hides this particular bit. And the answer to this question, unfortunately, is no, right? Because you can choose any I, and I can always design a one-way function which leaks I. Okay? For any I, a one-way function f might leak I. Okay, so this is unfortunate, right? I cannot even point to a single bit which f is not going to leak. So here's my new question. I have to be less ambitious now. And my new question is there any one bit function, let's say h of x, such that f of x hides h of x? So as an example, h of x might, let's say, XOR or AND certain bits and things like that, right? We can talk about any Boolean output h of x. Okay, so is it possible to construct some function h like that, such that any one-way function f is guaranteed to hide this h of x? So any thoughts about this? So again, the output of h of x is just a single bit. And again, the answer to this is no. There cannot exist a universal h of x such that f of x hides h of x, because, and the reason for this is, again, we can always construct another f prime of x such that f prime is just h of x concatenation of f of x, and this is just a single bit. So if f of x is a one-way function, then f prime is also a one-way function. Because giving a single additional bit of information is not going to help the adversary that much. If the probability of guessing x was negligible earlier, even given h of x, the probability of guessing x is still going to be negligible. Okay, and so h of x being one bit can't increase success probability of any adversary A, and hence this is also a one-way function. Okay, so So let me try to define a little more formally what we have been looking for. So the definition is hardcore. Let's write the definition in a different color. So the definition is hardcore predicates of a one-way function. So by the way, sometimes they're also called as hardcore bits or HCB. Okay. So by the way, a predicate is just a function with a single bit output. So a predicate H, which takes an n bit input and gives you a single bit as output, is a hardcore predicate for a function f. Again, this is a one-way function. Which takes an n bit input and gives you an output. If the function h is polynomial time computable, and for every PPT adversary A, what we want is that the probability that given the output of f, the probability that an adversary can guess the output of h is roughly half. So the adversary is given f of x, and the adversary has to guess h of x. We are looking at this probability such that x is chosen uniformly from the input domain. This should be, you cannot say this is negligible because it's just a single bit. I can always guess this bit with probability half. But what we want to say is that this probability is just half, right? Half plus negligible, not significantly more than that, right? If we can claim something like this, then we can claim that, yeah, indeed, h of x is a single bit, which this one-way function f of x hides perfectly in some sense. All right. And as we observed that no single construction of h of x is possible, which would work for every one-way function. There's a question, is this because it increases the probability of guessing by only a factor of 2? That's, yeah, that's exactly correct. Can't increase success probability of any adversary A by more than a factor of 2. Okay, so what do we do now? So here is our idea. So we will pick h at random. Whatever random means, we will see in some sense. Independent of the description of the one-way function f, then hope that with high probability f of x does not leak h of x. So this will be our hope. All right, any questions so far? And we will see that, in fact, this hope will, we will be able to realize this. So let me define the inner product function, and our hardcore predicate will be based on this inner product function. So inner product is also just represented as IP between some strings R and X is represented as X and R inner product is just equal to, and let me just write it in plain English. Okay, this is just summation xi ri over all I mod 2. Okay, I'm sure that many of you have seen this before. So essentially, R chooses a subset of the bits of X then you sum them over mod 2, or summation over mod 2 is also the same as XOR, or XOR the selected bits. So as an example, let's say the first bit of R is 1, every other bit is 0. Then we will just select the first bit of X, and the output will be the same as the first bit of X. And now here is the Goldreich-Levin theorem. I think it was 1987 or 88. Let me go with 88. So you are given a function f, which goes from n bits to m bits. Now sample R uniformly from 0, 1 to the power n. So R is a random n-bit string. Then you define the hardcore predicate h of x as just x inner product R. So this is a hardcore predicate of f with 1 minus negligible of n probability, and this probability is taken over choice of the random string R, or the choice of the predicate H. So what this theorem essentially says is that, sure, we don't have any fixed universal hardcore predicate. But as long as you choose your hardcore predicate at random in this way, independent of the one-way function f, then with very high probability, this will be a hardcore predicate for this particular one-way function f. Okay? So the full proof of this theorem is not something that we will be able to cover. I will just give you a basic intuition. The full proof is pretty long and complex. So we will just look at a toy case just to sort of build our intuition. And what is the intuition here? The intuition here is that suppose given the output of the one-way function, an adversary is able to guess the output of h of x, let's say for a large number of r's, or let's say for any r, then you can actually solve a system of equations to just completely recover x. Which would mean that the adversary has inverted the one-way function. Okay, so just in more detail. So towards contradiction, suppose there exists a PPT adversary A which can guess this inner product for any r with probability, let's say 1. So this would be the most extreme adversary. And by the way, one thing I should note is that the description of H, which in particular contains R, is public. It is given to the adversary. Okay, so the adversary is indeed given R, and the adversary has to guess this inner product of X and R. So now, yeah, so suppose you are given a very extreme adversary, which can just completely break your hardcore predicate in the most disastrous way possible, right? Just choose any hardcore predicate like this, adversary just breaks it with probability 1, can just guess the output with probability 1. Now, at least in this case, I can show you right away that that this adversary can also invert the one-way function, leading to a contradiction. Okay. So we will build another PPT adversary B to invert F, and in fact our PPT B will succeed with probability 1, in fact. Okay, so B takes f of x as input, and the goal of B would be to invert f of x. And B works as follows. So step 1 is choose R1 which is equal to 1 0 0 0. So this is an n-bit string, and only the first bit is 1. Every other bit is 0. Now use A to recover the inner product of X and R1. And now what is the inner product of X and R1? So this gives of X. So let me change the notation a little bit here. I don't want to. So let's call the first bit. We will represent the first bit as this. I. Now we recover X1, right? Because if you take the inner product of X with an R1, where R1 is 0 except in the first place, the inner product is just supposed to be the first bit of X. Step 2, you choose, and now you can already guess, right? 0 1, everything else is 0, and then you recover now X2, and then you keep going. Step n, since X is n bits, you will recover Xn, and now you have the whole X. Okay. And now B can output the preimage, and in fact, if A is successful with probability 1, then B will also be successful with probability 1. So this is just a very toy case. Now the question is, what if A guesses with probability, just let's say not 1, but let's say half plus noticeable of n, right? Another question I can ask is, what if A guesses only for a random R, but not for R's of this specific format, right? So the only guarantee that we have with A is that it guesses for a random R with probability half plus noticeable. So the intuition again in this case is that we will essentially try to use the same strategy, but now we will sort of have noisy equations. So in this case, we will end up with noisy equations. What do I mean by noisy equations? Some of the equations can be correct. Maybe more than half of them are correct, but many of them will be wrong because the guess of A can be wrong. And the question is, can you still recover X in this case? And the answer turns out to be yes. And by the way, this is also called as Goldreich-Levin list decoding. And this is not something which we can cover right now. So essentially what we have been able to do now is that given any one-way function, I can choose a hardcode predicate h such that h of x is essentially uniform given the output of the one-way function. And now we can hope to do great things with this because I have at least a single bit which is essentially uniform. to the adversary. So now we will move on to pseudo-randomness and how one might be able to design pseudo-random functions. So there's a question about the definition of inner product. What do you mean by R chooses a subset of bits of X over mod 2 near the definition of inner product? Okay. So maybe I should give an example of inner product. So what is the inner product of, let's take X to be 0, 1, 1, 0. And let's take R to be 1, 0, 1, 1. So let's look at R here. So here we have 1, so we select the first bit. Here we have 0, so we leave this bit out. Here again we have 1, 1, so we select this. Okay, so essentially we are summing 0, 1, 0, which is just 1. And once you take mod 2, it doesn't make any difference. So this R selects a subset of bits of X, and then you just sum all these bits. And how do you select a subset? The bits of R tell you which bits of X to select and which to leave out. As another example, suppose here we had 0, 0, 0, 0, which means that we don't select any of the bits of X, which means that the output is just 0. And if it was 1, 1, 1, 1, then you would just sum up over all the bits of X. So another question, can you explain why a universal hardcore predicate cannot exist? Good. So this brings me to this equation. So suppose there exists a universal hardcore predicate, which is h of x. H of x should work for any one-way function, right? So say h of x works for any one-way function. Now we will build a one-way function f prime such that h of x fails for a x prime. And how does f prime work? F prime of x equals just h of x concatenation with f of x, where f is any other generic one-way function. So there are two steps now. Step 1, we have to convince ourselves that f prime of x is a one-way function if f of x is. Okay? And this is not completely trivial, right? Because f of x guarantees that given f of x, you cannot compute x. But maybe given f of x and h of x, maybe somebody can compute x, right? So the proof of this is that f prime of x only gives h of x in addition. But this is only a single bit. But this can only increase guessing probability of X by a factor of 2. But this means that if it was negligible earlier, 2 times negligible is still negligible. So it would continue to be negligible.
Sir, can you please explain how does that factor of 2 comes? Like, how are you writing this that like it can only increase by a factor of 2? Like, where does the 2 come from?
Okay. So let's say I choose a 100-bit string. I ask you to guess it, right? You can guess it with probability 2 to the power minus 100. Now let's say I'm feeling generous. I want to help you. I will even tell you 1 bit of my 100-bit string. So how much can your success probability go up?
But it's not like I just know that 1 bit, right? I also know f of x. So I might figure out something from that and h of x, like.
So f of x is something which you knew even earlier, right? F of x is a one-way function, which means that given f of x, your probability of guessing was, let's say, 2 to the power minus 100, right? Now, in addition to f of x, I just give you a single bit.
Yes, okay.
How much can the probability go up from 2 to the power minus 100? F of x is something which you had in both cases, right? In case 1, you only had f of x. Your probability was 2 to the power minus 100. Case 2, you have f of x, and in addition, you have some one single bit of information.
So, but like it is a 100-bit string, right? So my probability will be a little more than 2 to the power minus 100, right? 2 to the power minus 100 is the probability when I have nothing.
Okay. So let's say I give you f of x, and let's say your probability of guessing x in that case is 2 to the power minus 80.
80, okay. So
Okay. So that's case 1, where you have
Right.
f of x. Your probability of guessing is 2 to the power minus 80. Now, in addition, I give you one more bit of information about x.
Okay.
Then your probability at most is going to be 2 to the power minus 79.
Yeah, why? Like, how are you saying this statement?
I mean, because this one bit is something, if I don't give you,
Right.
you can anyway guess this with probability half, right?
I still don't understand properly.
So say case 2, given h of x, your probability of guessing is, let's say it becomes 2 to the power minus 50 suddenly. Now, this is case 2. Okay, I hope you can read it. Now in case 1, now I can go back to case 1. I'm not given h of x, but I can just guess h of x, and I'll be correct with probability half. And now I'm in case 2, so it's half times 2 to the power minus 50, which is much better than 2 to the power minus 80. So the point is that if I just give you 1 bit, it's something which you could have even guessed on your own. So that's not something which is going to help you that much. Okay, anything else? There's another question. So the statement is supposed to be that for all f that takes an n-bit string, f prime takes in and returns an m plus 1 bit string, does this probability then increase at all? Yeah, so f prime does give you m plus 1 bit output. So this shows that, yeah, a universal h cannot exist which can work for any output length. But you can drop one of the bits of f of x, and again, that doesn't change things very much. And yeah, if I go into the proof of that, I think it will take very long. I can maybe explain it in office hours. And the reason we were failing earlier is because your f prime was actually dependent on h, right? And now in Goldreich-Levin theorem, what they did was you fix F first and then you choose H, right? So H and F, they are independent in some sense, and that's why we were able to succeed. Any other questions? Okay, so now we will try to do nice things using hardcore predicates. So first is pseudorandom generators. And these are also known as PRGs. So first, one of the points I want to make is that randomness is tricky / expensive in the electronic world. And why do I say that? So how do you generate randomness? In the physical world, maybe I just take a coin and I keep flipping, right? Every time I flip a coin, I can essentially generate one bit of randomness. That's or that's sort of the assumption, quantum says that maybe it's not true, but let's believe it is true. Now, in the electronic world, how do computers generate randomness? So they don't have any inbuilt coin. Essentially, it's like a circuit which is more or less deterministic. So computers use many factors to generate randomness, like the current temperature or what is the current temperature of the CPU, the last few keystrokes which you had, the movement of your mouse and things like that. And once you combine enough of these things, the hope is that the output is sufficiently unpredictable. And once you use like a random number generator in Python or whatever, this is basically the process it goes through. So this is a very heuristic approach to generating randomness. And in fact, what I can tell you is that many crypto systems broken because of a defective random number generator. And the point is that in cryptography, randomness is everything, right? I generate my secret key at random. If an adversary can guess my secret key, then there's just no hope to get any kind of security whatsoever, right? So randomness and keeping randomness secret and private in some sense is very important in cryptography, but it can be tricky. So what can we do, right? So let's say I need like 1,000 bits of randomness, right? Now a very natural question is, can I generate small number of random bits and then in some sense deterministically expand them to get a very large number of random bits? So can I generate, say, n random bits and deterministically expand to 2n random bits? So essentially, I'm looking for a function g, which takes an n-bit uniform output and it gives me a 2n-bit uniform output, and output of G is uniform. So now here's my question to all of you is, can such a deterministic function exist? Okay, good. So yeah, G can only have, the answer is no, because G can only have 2 to the power n different outputs. And why is this a problem? If I generate a 2n-bit uniform string, I will end up with like 2 to the power 2n different possible numbers. And here, if you do this in a deterministic way, you only get 2 to the power n. So drawing a picture here, these are 2 to the power n bit strings, and this 2 to the power n is a much bigger set, 2 to the power 2n. And if you apply so this is, let's say, your G. So if you apply G, then you only end up with a very small set of 2 to the power n size. And this is clearly not uniform. I will give you a test. So suppose we have two distributions. So say distribution x0 is output of G on n random bits. Distribution x1 is 2n random bits. And my test is just given distribution or let's say keep sampling from the given distribution. Say a very large number of times, let's say 2 to the power 100n times. See how many unique numbers you get. Okay, if I get at most 2 to the power n unique numbers, I know that the distribution is x0. Otherwise, the distribution is x1. Okay, so x0 and x1 they are not the same in any case, in any sense.
Sir, I have a small question. Why does G have to map an element on the left side to only one element on the right side? Why can't it map to randomly to a new element? Like,
it's a function. It's a deterministic function.
okay.
It takes an input and it gives you an output. If it is deterministic, then on the same input, it will always give you the same output. Right. So now a very good point. This test is very expensive. Okay, which brings me to pseudorandom generators, and that is exactly why pseudorandom generators are possible. So here's the observation that maybe if the test, or let's call it a distinguisher, is, let's say, probabilistic polynomial time, maybe there's a hope, right? Because let's say n is 100, you just cannot keep sampling so many times from the given distribution. And this will turn out to be correct. And this is why, you have these magical objects which can deterministically take like, let's say n bits, and you can expand them to 2n, 1000 and 1 million times and whatever you want, right? So this is like almost impossible when you think about it, but crypto makes it possible. So this also brings me to a very interesting observation, which is that when you look at like almost anything in crypto, you consider unbounded time adversaries, it just completely breaks down. But as soon as you go to polynomial time adversaries, everything just sort of magically falls into place. So this is very interesting. So what we are looking for here is in a PRG. So a PRG is again takes n bits, and for now I want to expand to 2n bits. And here this 2n is somewhat arbitrary. I could ask for any expansion factor. So I want to design a function such that output of G is what I would say computationally indistinguishable. From U of 2n. This is the uniform distribution on 2n bits. And this notion of computational indistinguishability is very important. It's probably the single most important definition, not only in this lecture, but maybe maybe like the first quarter of the course. It's very, very important definition. So now let me try to define what computational indistinguishability might mean. And for that, I will try to remind you of the definition of a distribution and what do I mean by two distributions being identical. Okay. So what is a distribution first? So let's say this capital X is a distribution, and every distribution has a support or a sample space. Distribution over support or sample space S if it assigns and typically it should be a non-zero probability. It's non-zero probability P sub S to an event small s in this capital S such that the sum of all these probabilities is 1. So summation over all S PS is just 1. All right, as an example, let's say X is a distribution of flipping a coin, right? So then the sample space is just head or tails, and the probability which is assigned to head is half, probability of tail is also half. and their summation is 1. Now let's talk about identical distributions. And then we will hopefully try to generalize the notion of identical distributions to computationally indistinguishable distributions. What I want to say is that two distributions, let's call them x0 and x1, are identical if for all s in, and sorry, so here S is also known as support of X, just notation. So S in support of X0 union support of X1. So you look at every possible event, and essentially the probability of that event in X0 and X1 should be the same. What I want is that probability of you sample X from X0 and I want to say that here for all, okay, I already wrote, sorry, for all S. X equals S. And now X is drawn from X1. Okay. So the probability of every event in X0 and X1 is identical. You take any event S. So is this clear? These are identical distributions. And now let me try to define what computationally indistinguishable distributions might mean. And this will be a failed attempt. Attempt 1. So a very natural attempt, right? Here we are talking about these two probabilities being identical. Maybe these probabilities should be very close to each other, like negligibly close to each other. Maybe not identical, right? So here's my attempt for all S, and then I will ask you for a problem, to point out a problem in this attempt. For every event in the support, X0 union X1, maybe the probability that X equals S such that X is drawn from X0 minus the same probability, but X equals S when drawn from X1. So maybe what I want is that these two probabilities should be negligible. Looks pretty reasonable, actually. But there are multiple problems with it.
So I think you need to sample infinitely many times to actually calculate those probabilities. Is that a problem?
No, not really. Shouldn't they both sum to 1? Yeah, I mean, x0 and x1 are still distributions. So they do satisfy this notion, and we will require that. So sure, yeah. The probability of all events will sum to 1. And in addition, for computational indistinguishability, we require this rather than this. Is this good or bad? And let me give you a hint maybe. So think of x0 as all even numbers and x1 as all odd numbers. Let's say n bit even and n bit odd numbers. So what is this probability? Let's say an even n bit number and an odd n bit number. So what is this probability? Half? No.
It's either 1 or 0 depending on what s is.
So note that this probability is defined for a specific s.
Yeah.
Right?
Or,
so this,
oh,
this
right. So, yeah.
So the problem now is that for a specific s, for a specific number, what is the probability that you get that number? It's actually really small, right? It's like
It's 1 over 2 to the n minus 1.
Exactly. Yeah. So it's either 0 or it's 1 over 2 to the power n minus 1. And I can say the same thing here. So that's already negligible, right? So the first observation is that clearly you give me samples from x0 versus you give me samples from x1. So this is clearly distinguishable, right? I can give you a correct answer with probability 1. I can just test if the number is even or odd. On the other hand, this probability here is either 1 by 2 to the power n minus 1, because this is the number of even numbers, or 0. If you pick s to be odd, then for x0, this probability would just correspond to 0. And similarly, this probability would either be 1 by 2 to the power n minus 1 or 0. So for any particular s, this, let me just copy this equation. So this is exactly 1 by 2 to the power n minus 1, right? If you pick an even number, this will be 1 by 2 to the power n minus 1, and this will be 0. For an odd number, here we will have 0, and here we will have 1 by 2 to the power n minus 1. So the difference between these two is 1 by 2 to the power n minus 1, but that is actually negligible, right? But still, we can clearly distinguish these two distributions. And why are we able to do that? Because even though for any specific s, this difference is negligible, there is an exponential number of s. So when you sum over all of them, this probability actually becomes 1 rather than anything negligible. Does this mean that sample space of identical distributions should be the same? Yes. From this identical distribution definition, it follows that sample space should be the same. Because if it is 0 in one, it should be 0 in the other, and vice versa. Okay, so I hope this example is clear. So this example essentially says that we are talking about events which anyway have very small probability, like negligible probability, then you cannot ask for the difference in probability to be negligible. That's just meaningless for any distribution. It will be negligible. So that's problem 1. So let's call it problem 1. There's another problem which is more of a syntactic problem, which is what is n here? If I start with two distributions, x0 and x1, there's nothing which is changing, no size of the input which is increasing or reducing, and so on. Right? So we really need to talk about a set of distributions or an ensemble of distributions. And in my example, I already did that. X0 was an n-bit number, right? So let me define what an ensemble is. So we will fix the second problem first, and then we will fix the first problem. So ensemble is a sequence of distributions, a sequence, capital X, N, N. So essentially X1, X2, X3, and so on. It is called an ensemble. So this is more of a technical point. It doesn't really affect our intuition or thinking very much. If for each n in the set of, so this is the set of natural numbers. X1 is a distribution. As an example, all n-bit even strings, or all uniform n-bit strings and things like that, right? So it's nothing fancy, just. Now I have just introduced a parameter n, and I can talk about things being negligible in n. And now let me try to give you the actual definition of computational indistinguishability. So computational indistinguishability definition. And this, as I said, this is probably the most important definition for today and maybe the next 1 or 2 weeks as well. I think there's a question. Okay, looks like, okay, great. Thanks, Justin. So what do we want? Very intuitively, what we want is that given the PPT adversary A, right? Maybe we give this adversary samples from X0, maybe samples from X1. This adversary should not be able to distinguish that. So I will just try to take this English sentence and I'll just try to put it in more mathematical terms. So what I want is that for every PPT adversary A, I look at the following two probabilities, and I would ask these probabilities to be very close to each other. Probability that AS outputs 0, where S is coming from, let's say, X 0n. Oh, sorry, 550. So two ensembles, x0 and x1. Are said to be computationally indistinguishable if for every PPT adversary A, the following holds. So first I am sampling from S0 and I am looking at the output of the adversary. What does adversary think of this sample? Next, I will sample from X1. And I would ask these to be very close to each other. So now let's look at this equation. The probability that AS outputs something specific, let's say 0, remains the same whether it was given this type of input or it was given this type of input. So that's sort of a more convoluted way of, or maybe a less natural way of saying that the output of A doesn't change if you change the input, which essentially means that A is unable to tell the difference between inputs of the first type and the inputs of the second type. Okay, so essentially, output is independent of, I should not say independent, but output doesn't change if input does. So now, just as a sanity check, let's go back to our even strings versus odd strings examples, right? So now I can obviously construct an adversary which just checks if a string is even. If it is, it outputs 0, otherwise it outputs 1, right? So now let's say I'm sampling from the even string distribution. Then this adversary will always output 1, and hence this probability is 1. On the other hand, when I start sampling from the odd distribution, the probability of this is actually 0, because adversary A always outputs 1. So I'll have 0 minus 1, which is, you take the mod, that's 1, not anything which is close to negligible. So any questions? We will see another natural definition and we will compare the two definitions. Okay, so let's see another definition actually. The definition, so in general, maybe distributions are not computationally indistinguishable. So this quantity is known as, let's call it the distinguishing advantage. So if the distinguishing advantage is negligible, we call the two distributions to be computationally indistinguishable. And by the way, for simplicity, we will just essentially drop this curly brackets and n, and simply we will use x0 and x1. And we will implicitly keep in mind that these are actually distribution ensembles rather than just a single distribution. Okay, so now let's move on to another definition, and we will try to compare the two. So this definition is called prediction advantage. And this might be a more straightforward way of defining things. So in prediction advantage, we ask the adversary to just predict which sample he got from x0 or x1. The adversary just has to guess this fact. And we look at the probability that the adversary is successful, right? So any adversary can, of course, guess and be correct with probability half, but we don't want this probability to be much more than half. So we say that distribution ensembles x0 and x1, and again I'm dropping the curly brackets and the n, have prediction advantage epsilon if for every PPT adversary A, we are looking at the following probability. So A is given some sort of sample. And X could be coming from x0, sorry, xb, so B is first picked at random, and then the sample is given from xb. So we are looking at this probability, right? An adversary which doesn't even look at the sample can be correct with probability half. So we are interested in seeing how much this adversary is able to do compared to half. And we need this to be not negligible, we need this to be epsilon. And if epsilon is negligible, x0 and x1 have prediction indistinguishability. Okay, so this might seem like a more natural definition. I have two distributions, I pick one of them at random, adversary sees a sample, and then adversary has to tell me which distribution I started with. But these two definitions are actually equivalent. So here is a lemma. So lemma says that if x0 and x1 have computational indistinguishability, then they also have prediction indistinguishability. And the proof of this is, it's not difficult. It's mostly elementary probability calculations. So say x0 and x1 indeed have computational indistinguishability, right? In that case, sorry, have prediction indistinguishability. In that case, I need to prove both directions. So in that case, probability that AX equals B is sampled at random, and X is sampled from XB in that case, minus half. So this is guaranteed to be negligible, and let me just try to write this in a slightly different form. So this is AX. So we will just expand these into two cases. Case one where B equals 0, and the other case is when B equals 1. Into probability that B equals 0 plus AX equals 1, and the sample is chosen from X1 now, and the probability that B equals 1, right, minus half. So is this, hopefully this is clear. And by the way, this is half, because B is a uniform string. So I'll take half outside. And then I just have probability of AX giving me 0 such that X comes from X0 plus, I'm looking at this probability now, and I can write it as 1 minus probability that AX gives me 0 and X comes from X1. What is the probability that AX equals 1? 1 minus the probability that AX equals 0, because the adversary is supposed to output either 0 or 1. Okay, and then minus 1. So this 1 and 1 will cancel out. And this expression is exactly the distinguishing advantage. So this is half times the distinguishing advantage. Okay? And I think I didn't use inequality anywhere. This is all equality. So this implies that if one is negligible, so is the other. So in fact, they are within factor of 2 from each other. Right? So, you know, what is true between friends, right? In the bigger scheme of things, looking at advantages, looking at asymptotics, this factor of 2 doesn't really matter at all. So why did we use the computational indistinguishability as opposed to maybe the more natural prediction advantage? So we prefer the computational indistinguishability definition because it's much nicer. What do I mean by much nicer? Let's leave that to next time. Next time, we will see very nice composition properties of this computational indistinguishability definition, which means that you don't really have to go into the exact math, exact probability most of the time. Once you build the right intuition about it, you can almost think about it as you would think about some argument in English. Okay, so we will see some of these composition properties next time.